Good evening, everyone. I am Mr. Ish. We're looking here at the use of Maclaurin series expansions for limit evaluations. A very interesting and useful adjunct topic for limit evaluations. Imagine you're evaluating something like this. Limit as x approaches 0, you have sine x divided by x. You know it's a rational function. You put 0 in place of sine. You evaluate 0, 0, you get an indeterminate limit form, and then you would normally do another procedure, derivative of the numerator, derivative of the denominator, then plug in the 0, and you'd have an outcome. But you can use a Maclaurin series as well for these type of questions, and I'll show you how. Not just only these type, but other similar types. I'm just showing you in this video a few types. But to do that, then you have to see the series of that, and you know the series is very quickly established using this form. We won't spend too much time going through all of this because we've seen it. We will breeze through it. You know, right there is the template for developing the series expansion for sine x. You would have to develop the derivative forms, the higher order derivatives. You know, the original function is the 0 order derivative, and that right here will be just sine, and then you're looking at 0. The first order derivative would be cosine, and then you're putting a 0, because you know you're always putting an a value of 0 when you're looking at this type of series centered around 0. As you know, the Maclaurin series is centered around 0. The second order derivative, if that is a minus sign, but you're putting a 0. The third order derivative is a minus cosine, but again, you're putting a 0. The fourth order derivative, and I'll stop over there. Remember, these are all the higher order derivatives of this sine x, because we're developing the series for that. Would be a sine, and then you're putting a 0. Here you're getting a 0, here you're getting a 1, here you're getting a 0, here you're getting a minus 1, and then a 0. You'll put everything right in here. The sine x will expand in the following way. When centered around a equals 0, it will expand this way. You'll have 0 times x to the power of 0 over 0 factorial, which is just a 0. Then you'll have 1 times x to the power 1 over 1 factorial. Then you'll have here a plus 0 x to the square over 2 factorial. Then you'll have a minus, I'm right over here, a minus x cube over 3 factorial, and you know there's a 1 coming in. I'm not putting the 1. And then we're right here, you'll have a 0 x to the 4 over 4 factorial. When you iron all of this down, the sine x expansion in terms of the Maclaurin series, and here we're looking at the Maclaurin series polynomial 4, it would become what? It would become a 0 plus x plus 0 minus x cube over 3 factorial plus 0. And then you clean it out some more, you have x minus x cube over 3 factorial. You put in some more higher order derivatives, and then you start seeing a pattern develop, and this right here is a pattern. It's an alternating positive minus with odd number exponents and odd number factorials. All of that comes into play, and this is exactly what it looks like. So I've developed this expansion. In this limit question over here, wherever you have a sine x, you can put this. So how does everything play out? Limit as x approaches 0, sine x divided by x. I'm getting this. So how do I bypass that problem? This problem right here, I use a series. Everything becomes this. You have x minus x cube over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial. You don't need to keep going on. All of this is divided by your x variable. And bring x into everything here. We're into each of these items. Divide each of these items by x. X divided by x. This x divided by x, you get a 1. This divided by this, you'll have a minus x squared over 3 factorial. This factor here divided by x will be plus x to the 4 over 5 factorial. This with that, you'll have a minus x to the 6 over 7 factorial, and it would go on and on. Limit as x approaches 0, d0, d0, d0. The only thing which remains is a 1, and your limit answer here would be 1, and it would be right. And you've done it using this way. You know, if you did the derivative of this, you have a cosine x. You do the derivative of this, you have a 1. Cosine x over 1 is a cosine x. Put 0 into cosine x and you get a value of 1. That's the L'Hopital's rule of doing it, but here you're now seeing it in a whole different way, and this right here is a very good way. So what's the caveat or the condition for this video? You're seeing I'm presenting you questions over here, limit questions, which are involving functions which are centered around 0 in terms of me using the Maclaurin series for these series expansions. I could make it more complex and use Taylor series. I don't want this video to be too long. But look over here, limit as x approaches 0, we have sine hx over x. You put 0 on each of these, you're looking at a 0 over 0 form. But you can utilize the Maclaurin series technique for doing these type of limit evaluations. You just have to develop the series for that, and it's not hard. The zero order derivative is equal to your original function, which is just sine h, and I'm putting 0. My a value here are always 0 because everything is centered here around 0. The first order derivative here is a cosine h. You know, the sine and the cosine alternate in terms of their derivatives. Every other round they're alternating. The second order derivative is back to the sine h. The third order derivative is now at the cosine, and then the fourth order derivative is back to the sine h, and then a 0. This is equal to 0, this is equal to 1, 0, 1, 0. The difference between the hyperbolic sign and the trigonometric sign is that here everything is positive. In the trigonometric sign you have the alternating of the signs as well. But in terms of the exponents and the factorials, they're always odd numbers. When you expand all of this by means of this, what will you have? The hyperbolic sign, when it's centered around a 0, will develop a series which will look like this. You'll have a 0. The first term is a 0, but the next term will be 1, x to the 1 over 1. The next term will be a 0. I won't write all of these other terms because they're zeroing out anyways. The next term is this, 1x cubed over 3 factorial, and then the next term is a 0, and then you can extrapolate the rest. Your series is x plus x cubed over 3 factorial plus x to the 5 over 5 factorial plus x to the 7 over 7 factorial. You see the difference between the sign expansion that had negatives come in every other terms. This is exactly like that, but everything is positive. Bring everything into this limit evaluation. Limit as x approaches 0. Bring all of this. This right here represents your hyperbolic sign along with everything else, and then you have the x here. You'll do x plus x cubed divided by 3 factorial plus x to the 5 divided by 5 factorial plus x to the 7 divided by 7 factorial, on and on, divided by x. You would individually manipulate these terms and divide everything by x. This by x, that by x, that individually by x. X divided by x, I'll get a 1. X cubed and 3 factorial divided by this, I'll have plus x to the square over 6. I'm getting rid of the factorials. This will become plus x to the 4 over 5 factorial, which is 120, plus x to the 7 divided by 7 factorial, and this would be x to the 6 over 5040. These zero out as x approaches 0, but this does not 0. Your answer for this limit question is a 1. And all of this right here in terms of a limit will be equal to 1. You could have done the L'Hopital's rule. Derivative of this is hyperbolic cosine of this is 1. You have a hyperbolic cosine feeding the 0 value, and you get a value of 1. So that question is done. Let's look at one more question, and we'll make that slightly more complex. But again, the theme of this video is you can use a Maclaurin series idea, this whole concept of the Maclaurin series, to develop a series, and you use that series, which is really a power series. You're using a power series here of a function to help you evaluate a limit. We have this limit as x approaches 0, hyperbolic sign minus x divided by x cubed. You know, if you put 0 in places of this, you're looking at 0 minus 0 over 0. You have an indeterminate limit form of 0 over 0. I want to use a Maclaurin series, but I'm not going to reduplicate all of that. I know what my series is because I've just shown it to you. The hyperbolic sign series looks like x plus x cubed over 3 factorial, which I'm writing as 6, plus x to the 5 over 5 factorial, I'm writing 120, plus x to the 7 divided by 7 factorial, 5040, plus x to the 9 divided by 9 factorial, and onwards. So you've seen the series, and that's what it is. You have to bring that in here, and it's not hard. We just have to do a little bit of manipulation here because we have these extra, well, we have this extra term. And yeah, hyperbolic sign is equal to that. Let's bring the hyperbolic sign. It's x plus x cubed over 6 plus x to the 5 over 120 plus x to the 7 over 5040. You can just do a good assumption here. You don't have to keep going because everything will eventually zero out. This minus that x. This is my numerator component. Here's my denominator. How do you simplify this? Open up the numerator. When you open up the brackets, it's no different than you just looking at this. You've opened up the parentheses, and you can cancel this with that because you're looking at a x minus x. It's in this grand scheme, you can just open and work on the numerator. What you end up seeing is now a limit as x approaches 0. You have x cubed over 6 plus x to the 5 over 120 plus x to the 7 over 5040 plus on and on divided by x cubed, which is the denominator component right here. Now you individually apply x cubed to all of these. You'll have an x cubed divided by 6 divided by x cubed. You'll have x cubed divided by 6x cubed. This is really x cubed over 1. You flip it on, you multiply with each of these items, that's what you get. Here you'll have x to the 5 divided by 120 x cubed. We'll add this next item, x to the 7 divided by 5040 x cubed. On and on. This will cancel out with this, you'll have 1 over 6. This will cancel out with this, you'll have a square. This will cancel out with this, you'll have a 4. But all of this will zero out because you still have an x here in the numerator. All of this will zero out because limit as x approaches 0, these zero out. The only thing which does not zero out is this, but this already gave you a value 1 over 6. The answer to your limit value here is 1 over 6. And it indeed would be right, because if you had used the other way, you would actually come up at that same conclusion. I can show you that, and I'll show it to you right over here. But as you saw, for this specific question, we use a Maclaurin series route for limit evaluation. I can show you how you would have done this using the L'Hopital's rule. If you had done the derivative of this numerator and then the derivative of the denominator component, and you would keep repeating that procedure until the indeterminate limit form is no longer repeating or showing up, then you would do your plug-in value and do your limit evaluation. Well, let's see what happens. You'd have a cosine hx minus the derivative of x is just a 1 over 3x squared. You would put a 0, what would you get? Well, you'd have a 1 minus 1, which is a 0 divided by 0. You'd have a 0 over 0. So you could technically do another round of derivative procedures, and you would. The derivative of this would be a sine hx, and the derivative of that is a 0, and the derivative of this would be a 6x. You'd put 0. You'll have a 0 over 0. You're still seeing the indeterminate limit form, so you can do yet another round of derivative procedures. And you would. The derivative of that would be a hyperbolic cosine. The derivative of 6x would be a 6. Now you put 0. When you put 0 here in places of x, you'd have a 1 over 6. And your indeterminate limit form of 0 over 0 is no longer present, and you stop because you've arrived at a finite value. 1 over 6 is it. 1 over 6 is right by both ways. And we now come to the conclusion of this video. The Maclaurin series can be used to expand a function. That function, when expanded into a power series format, can help you do limit evaluations. And that is the theme for this video. Thank you for watching.